All right, guys, here we go. We're about to do this crash course, linear functions, all the things for this chapter. So the very first thing that we talked about, kind of the most important thing about a linear equation is slope. We can find slope a couple of different ways. The most useful way, I think, is the slope formula, which is just y minus y over x minus x. And I'll come back and do a little example like that in just a second. But we can also find slope from a table by figuring out the change in y. So like from 3 to 11 is 8. 11 to 19 is 8. And they're all going up by 8. And then also finding the change in x. So from 0 to 2 is 2. 2 to 4 is 2. 4 to 6 is 2. 2. And so we do the change in y, like delta y, over the change in x, so 8 over 2, which is 4. But if you don't want to do all that, like you can just pick 2 points, like we would do here, and do our little slope formula. So if I pick the point 0, 3 and 2, 11, I would put y in for y and x in for x, and you can really choose. Like I don't really want to do 3 minus 11, because that'll give me a negative. I'm going to do 11 minus 3, but because I subtracted this way, I also have to do that with my x's. So 2 minus 0, which 11 minus 3 is 8. 2 minus 0 is 2. Divide them out, it's 4, just like we got before. Now we can also find slope when we're looking at a graph by counting the rise over run. So you have to find 2 really nice points. And when I say really nice points, I mean points that go through the crosshairs of the graph. So as I look along this line, I see one really good one right here. And then another really good one right there. And so if I count how much I need to go up or down, I actually need to go down 1, 2, 3 squares, and down is negative. Excuse me. And then I need to run forward 2 squares, and forward is positive. So this slope here is negative 3 over 2. Now, after we talked about slope, we talked about direct variation. Direct variation is the most basic linear equation that we have. It's written like y equals k times x, where k is really slope, but it's better than most slopes because no matter where I go on the line, it's always the same. So another really important thing that we did with direct variation was that we would say that y over x is equal to y over x because they're always changing the same amount. And this was helpful because if they gave me a point like 1, 5 and 2, y, and I needed to solve for y, we can just do y over x, so 5 over 1, equals y over x, so y over 2. And you might be able to just see what the answer is, but we can cross multiply and solve. So 1 times y is 1y, 5 times 2 is 10, and y is alone, so y is 10. Now, the other really important thing about a direct variation graph is that it always goes through 0. And so if we had the equation y equals 2x, it starts at 0 and has a slope of 2. So up 2 over 1, up 2 over 1, and you get a really cute looking line like that. Next. It was all about the forms of the line, guys. So we're writing equations of lines. A really good one to use is point slope form. It's very versatile. It looks like y minus y1 equals m parenthesis x minus x1, where m is your slope. And hopefully they tell it to you. But if they don't, you're going to have to find it by doing this. And then your x1, y1 is a point somewhere in space. And so that's literally why we call it point slope form, because I can see a point and I can see the slope. So if they tell me that the slope is 3 and it goes through the point 2 comma negative 4, if I'm going to write that equation, I'm just going to bop in all the numbers where they're supposed to go. So y minus the y value, which is negative 4, and the double negative will actually make it a plus, equals slope, which they told me was 3, parenthesis x minus the x value, which is 2. And really, you can leave it like that, but if you needed to rewrite it in any form, you could distribute and get the y alone. Now, if I were to graph this, I would want to plot the point, which is 2 comma negative 4. So 2 comma negative 4. And then I would do the slope, which is 3. So up 1, 2, 3 over 1. 1, 2, 3 over 1. So you get that little cutie right there. Another form of a line, probably y'all's favorite, is that slope-intercept form. That is y equals mx plus b, where m is your slope and b is your y-intercept. And that's why we call it slope-intercept form, because those are the numbers that you can see. So if you're real lucky and they tell you that the slope is negative half and the y-intercept is negative 3, you can just boop those numbers right into your equation. So you'll have y equals negative 1/2 x minus 3. Now, if they don't tell you that, if they don't give you the y-intercept and they just give you a point, well, then you should put it in point slope form and then distribute and get y alone. If they don't give you the slope either, then you got to go all the way back to the start and find the slope and then put it in point slope form and then change it to slope intercept form. So if I were to graph this one now, I would want to start on my y-intercept, so on my y-axis at negative 3. And then my slope is telling me to go down 1, forward 2. Or another way to think about it is to go up 1, backwards 2. So that we get this negative slope. Last form of the line that we had was standard form. That was ax plus by equals c. And unfortunately, the a, the b, the c, they weren't any useful numbers. But some of the things that we did have to be careful about here is that a, b, and c all need to be whole numbers. No fractions allowed. So we multiplied by the denominator to get rid of it. And a needs to be positive. So if it wasn't, we multiplied everything by a negative to make it positive. But there was kind of an easy way to graph something that was already in standard form. So if I had something like 3x plus 2y equals 18, I could easily find the x and y intercepts by just ignoring the other letters. So if I wanted to find the x-intercept, I just ignore y, and I have 3x equals 18, and if I were to solve for x, I divide by 3, so x is 6, and I go on the x-axis and plot a 6. Then if I wanted to find the y-intercept, I ignore x, and I write what's left, so 2y equals 18, and if I have to solve for y, I got to divide by 2, and y is 9. So I go along the y-axis. Why did I do this? I don't have a 9 here. 7, 8, 9. And then we connect the dots. Cute. Then, after we talked about all the forms, we also really talked about parallel and perpendicular lines a lot, and those are really important too. So with a parallel line, these are lines that never cross or never touch, but more importantly, they have the same slope and different y-intercepts. They are traveling at the same speed up here so that they can't touch each other. And they have to have different y-intercepts, again, so that they're not touching each other. Now, with perpendicular lines, these ones do cross, specifically at a 90-degree angle, but really more for our purposes, we needed to know about the slope. And for perpendicular lines, the slopes are opposite and reciprocal. Which what opposite means is one is positive and one is negative. And what reciprocal means is I flip it over. So if it's 3/4, now it's 4/3. Okay, and if it's just a number, there's always a 1 under. So like if it was 3, when I flip it over, it's 1/3. Okay, now this was important because if they said, write the equation of a line that is write the equation parallel to y equals 3x minus 1 and through the point -2 comma 0. Wow, sure, making it up. I would need to write a brand new equation. And since I want it to be parallel, I have to have the same slope. So my slope also needs to be 3 because this guy's slope is 3. And I need to go through the point -2 comma 0. So thinking back on what I have, since I have a point and the slope, I'm going to put it in point slope form. So I would do y minus y, which is 0, equals m parenthesis x minus x, which is -2, so really plus. But then if I wanted to put it in y equals mx plus b, we would distribute. So 3x plus 6. And then I'd add the 0, but I mean, it's just 0, but we want to get that y all alone. And there you go. Now, another example of a perpendicular case is if I wanted to write the equation perpendicular to, or upside down t, to y equals 3x minus 1, and through the point -6 comma 1. Again, just like the last one, I need to use that point, -6 comma 1, and I need to do something with the slope. Now, this time, because I'm perpendicular, my slope is not the same. It needs to be the opposite. So this one's positive, mine will be negative, and reciprocal. So since it's 3, I need to flip it over for 1/3. So again, because they give me a point and slope, I'm going to put it in point slope form. So y minus the y equals m parenthesis x minus the x, which is a double negative, so plus. And then we want to distribute so that we can put it in y equals mx plus b. So we'll have -1/3 x, and then a negative times a positive is a negative. 1/3 of 6 is 2. And then get y alone by adding 1. So y equals -1/3 x minus 1. And then the last thing that we might ask when it comes to parallel perpendicular lines is, are they parallel, perpendicular, or neither? And you got to check the slope to see. The reason I want to leave it at just that, guys, is because I want to remind you of a couple other things down here. We had those scatter plots, which remember, if they were all kind of dotties going up, we had positive correlation. If all the dotties were kind of going down, we had negative correlation. And if it was just a splat of dots, not doing any particular thing, we had no correlation. And then the other thing to mention is our inequalities. So we want to remember too about inequalities, and that if I had a greater than or less than, we would get a dashed line. And if we had greater than or equal to or less than or equal to, we got a solid line. And then if I had a less than or equal to, so either line, doesn't matter, I had to shade below. And if I had greater than or equal to, I had to shade above. Crash course, it's a lot. You can do it. Hopefully you have your notes and you can look back at them. And if not, hopefully this helps too.